Graph Theory Class 5 Video 2. In this video we're going to talk about isomorphic graphs. The notion of an isomorphic graph, it's similar to that of an equal graph, except isomorphic is sort of like a weaker condition. To be equal, you care that they have exactly the same vertices and exactly the same edges. But to be isomorphic, you just care about more of the underlying mathematical structure. So superficial qualities like what you actually call the vertices, the names of the vertices, aren't taken into account when considering isomorphic graphs. So let's just go to the formal definition. So we say that two graphs are isomorphic if there is a labeling or a relabeling of the vertices so that they're equal. Okay, so two graphs are isomorphic if it's possible to change the labels so that they become equal. And obviously you can't always do this. Not every graph is isomorphic to every other graph. So a really simple example, if I label this A, B, C, and I label this one W, X, Y, Z, there's no way you can relabel the triangle to make it the square, right? You could try to cross out A and maybe label it X, Y, Z, but you're still missing a W, right? So these two graphs here are not isomorphic. But if I was to redraw the second graph just like this, now they are isomorphic because it's possible for me to cross out the labels, relabel the second one so that they become equal. That's what isomorphic means. Isomorphic, you ignore what the vertices are actually called. And in fact, they don't have to be called anything. You can talk about isomorphic graphs which are not labeled. Okay? The most important thing to keep into account is that isomorphic graphs only care about the underlying mathematical structure. Okay? So isomorphic graphs have exactly the same mathematical structure. But the vertices might have different names. Okay, so isomorphic graphs, you throw away all of the superficial information, like what the graph represents from the real world. So if we think about like the Alice, Bob, Charles, David, Eve, and Frank, and who fancies who, that's extra data coming from the real world. Isomorphic graphs would just throw away all of their names. It doesn't care about what they're called. It just cares about the mathematical structure of the graph. Okay. So let's do some examples. So if we look at these three graphs here, these three graphs are actually isomorphic. And to show they're isomorphic, I'm going to show that they're all isomorphic to the first one. Okay? Which means I need to show that there is a relabeling of the second and the third to make it equal to the first one. Well, it's pretty simple, I think, especially the first, showing the second one. I just relabel this A, B, C, D. And now these two graphs are equal, which means the original graph was isomorphic. Okay? Let's move on to the next one. This one's a bit trickier, okay? It would be incorrect to do A, B, C, D. This is incorrect because if we consider the left graph, we see that there's no edge between A and C. But if we consider the rightmost graph, there is an edge between A and C. So this is an incorrect labeling. Okay, that's an incorrect labeling. But there is possible to find a correct labeling. I could label this A, okay, and let's just follow the edge. So this edge here, now the question is, what do I label this? Well, it's going to be something which is connected to A. And if I look at my original graph, I could label it either D or B. It doesn't matter which one I choose in this situation. I'll label it B. Now I'll follow this edge. Okay, what's connected to B? In the original graph, B is connected to A and C. So B is connected to A, which means this thing here has to be C. And finally, this down here, the relabeling has to be a D. Okay, so now this relabeling does make the graph equal to the first graph. Yeah. Also, I could have just drawn this without any labels at all, and this is still isomorphic to all of the above. Isomorphic graphs don't care about labels at all. All that matters is, like, is it possible to give them labels so that they become equal? So let's move on to a slightly harder example. Show that these two graphs are isomorphic. That's what I want to do. Okay. Well, the one on the left has labels already, and the one on the right doesn't have any labels. So I'm going to try and label the one on the right to make it equal to the one on the left. I'm going to throw down A, and since it's a symmetric graph, it doesn't really matter where I choose. I could have put A anywhere. It doesn't matter where I choose to put A. So I'm just going to put A at the top. Now I'm going to consider what's A connected to. So I want to know what goes down here. I go back to the original graph and I realize A is connected to B and E. So it could be, I could put either one of these. I'll put B there. Now, what's B connected to? B is connected to A and C, which means that this here is C. C is connected to B and D, which means this is D. D is connected to C and E, which means this is E. And finally, just to check, E is connected to A and D on the left, and on the right, E is connected to A and D. So this is a relabeling of the pentagram so that it becomes equal, which means the original graph was isomorphic. Okay. In these sort of questions, by far the hardest part is finding the correct labeling. It's non-trivial to find the correct labeling. And there's not really like a secret method which works every time. It's a lot of trial and error, okay? You have to try and just match up the left graph to the right graph, okay? Another way you could possibly think about doing this is you could try and mentally rearrange the vertices of the left graph to make it look like the right graph. If you can do that, then that gives you the answer. If you can imagine moving like these vertices around, okay, just stretching and pulling this left graph to make it look like the right graph, then that will give you the correct labeling. But sometimes that's hard to do. Yeah. In this particular case, it's hard to see how to rearrange the left graph to get the right graph. Okay, let's do one more example. So this example is even harder. Show that these two graphs are isomorphic. Okay. So how can I even begin to do this? Well, it's just trial and error and luck. Okay. I'm going to begin with A because A just seems like a nice thing to begin with. And I'm going to notice like there's an A down here. I'm going to put it up the top for no particular reason at all. Okay. And now on the left, A is connected to D, E, and B. So on the right, I'm going to just connect A to D, E, and B. And I'm doing this pretty randomly, and I'm just hoping that it will work out in the end. Okay. Now, what can I do? Maybe let's consider what's B connected to. On the left, B is connected to A, E, and C. But this is a problem if you think about it, because on the right, B is not connected to E. There's no edge here. Okay, but on the left, B is connected to E. So that means my labelings are incorrect. Okay, so back to the drawing board, back to the beginning. So I have A, and I know it's connected to D, B, and E. And my original attempt was incorrect, so I just have to try again. Okay, how about this time I try and do B, E, and D. Okay, I just changed how I put them down. So now let's try again. So on the left, B is connected to A, E, and C. On the right, B is connected to A, E. So this is good news. This is good so far. And the last thing it needs to be connected to is a C. So it means that this vertex here has to be a C. Okay, so that's A and B done. Let's look at C. So on the left, C is connected to B, D, and F. And on the right, C is connected to B, D. So the last thing it needs to be is an F here. Okay, I shouldn't stop. I should check that everything makes sense. So on the left, D is connected to C, A, F. And on the right, D is connected to C, A, F. So D is okay. Now let's look at E. E is connected to A, B, F on the left. And on the right, E is connected to A, B, F. So E is okay. And finally, let's look at F. So on the left, F is connected to C, D, E. And on the right, F is connected to C, D, E. So this labeling is the correct labeling. It's a labeling such that now the left and the right graph are equal. So that means they were originally isomorphic. Okay, like I said, finding the correct labeling is 95% of the work. It's the hardest part by far, and a lot of it is just trial and error. Okay, that's the end of this example, and it's the end of this video.